Hello. This is day one of a graph theory unit. And so this is all about modeling with graphs, and it kind of changes our perspective of what is meant by a graph. And it kind of starts off, we need to know certain terminology, like what an edge means and a vertex. So there's the Königsberg bridge problem, and there's a dodecahedron problem, where in the Königsberg bridge problem, we want to know if it's possible to travel through every edge exactly once. So here's what an edge is. An edge is labeled in each of these in purple, and it's basically, we would think of it as a connecting line between 2 points, and the points are called, a point is called a vertex. So you can see that you have vertices A, B, C, and D in the red dots, and edges A, B, C, D, E, F, G. All right, so here's the Königsberg bridge problem. We want to know if we can get started anywhere you want, but we have to travel every edge exactly once. So you could try something out. We could say, let's start at A. I go to D, to C, and now I'm kind of stuck because if I go, it says to be exactly once. If I go back to A, I still am going to have to get C somehow. So I could get it now, but then I have to go travel either back through D or through G, and it's already been traveled. Or maybe I can forget about C for a second. I could go down to B, and then I could certainly go, A and then C, but then I didn't cover F. So if I didn't do that, maybe I could go down to B and then down F, but then I can't go anywhere from there. So you should try that and see if you can figure out a way to do it. Solution to these will come up later. So I'm going to leave you hanging for a second. And there's also a dodecahedron problem, where we want to travel every vertex exactly once. So we just need to hit each of the red dots once. All right, so I'll just try one example. This may or may not work, but give it a shot. We'll start there, and let's go vertex, vertex, vertex. Oh, I did it. Okay, so I wasn't sure it was going to work. I was just showing you how you could try it, and that one ended up working. There are multiple solutions to this one, but so you should try it out on your own. Okay, so really this is just introducing you to what a vertex and an edge is. They will be a main player in this unit. Okay, here's another example, just kind of a fun little problems. One mailbox is located at each intersection of a city, and a postal truck is required to collect the mail from all the boxes in the 42 block region in the map at the right. Can the driver plan a pickup route that begins and ends at the same place? So that's interesting. And allows collections of the mail from all the boxes without passing one that has already been collected. So basically just means no repeats. And mailboxes, they appear at the dots, so this is going to be no repeated vertices. That's essentially what that means. And it begins and ends at the same place. So see if you can figure out a way to do this. You may want to pause it. Okay. I'm going to try this. Again, I might not do it right on the first attempt, just like most of us wouldn't, but just give it a shot. See, I have to end where I started, so I don't want to go all the way back up, because then I'm going to have to repeat some vertices. So let's try this. Okay, I guess that worked. Again, there'll be multiple variations of this, but that's what is meant. We had to travel through every vertex once, exactly once, and start and end at the same spot. Okay, there's going to be a name for that later on, but just another different example. Ooh, okay. These are interesting. It's another type of a graph that we could think about. So it's a scientific experiment, involves the following tasks. And then each of these tasks have a certain amount of time that it takes for the task to complete. And some of the next tasks that you could do require a previous task to be complete. So for instance, I can't start a task E until D has been completed. D I can't start until B and C have been completed. So we can kind of maybe draw some type of task graph that shows just a visual representation of this about, and we could also figure out how long it's going to take, because we can't just count up the months, because some of these tasks could be completed concurrently. All right. So here is a graph that kind of shows how this would look. And we could look at the graph to determine the least number of months to complete the experiment. So we'll zoom out a little bit so we can see more of it. You'd see that you can start A, and the 1 means it takes 1 month to complete. But we can start A because there is no prerequisite for A. That's the starting one. B and C both require A to be done. So they are branches. Once A is complete, then we would start B and C, because they both just require A, so we would start them as soon as possible. B takes 1 to complete, C takes 2 to complete. We can't get to D until both B and C are complete. So then these both need to be complete for D to start. It takes a half a month. And then notice there's 2 of them that require D to be done, so we would start both E and F once D is complete, E and F. And it takes 6 and 5.5, but we can't start G until both E and F are complete. So G, and then it takes 1, and then we'd be done. The least number of months then, some of these happen concurrently, so we don't just add up how long everything takes. We'd say this one is 1. These happen concurrently, so B would be done already when C has 1 more month left. But D can't start until both of these are done. So B would be done first, but we still have to wait for C, and it takes 2 months. Then D is going to complete in 0.5. E and F, they both can happen concurrently, and they both are waiting for D to finish. So once D finishes, they both start. And F is going to finish a little bit quicker than E, but G can't start until they're both done. So G is going to be waiting on E, essentially, because it's longer. And then G takes 1 month. So in this case, we could add all these up, and that's how many months it would take to complete this. And this is it's a useful graph because it shows which ones can happen concurrently, and you can more easily see the total time it takes actually. So like 10 and a half. All right. So these are a lot of just varying examples. They seem very unrelated to each other, and that's the purpose, just to kind of get us used to thinking about graphs in a different way. This is kind of almost like a probability tree. So suppose that 75% of a bushel of apples are Honeycrisp, while the rest are Sweet Tango. 80% of the Honeycrisps were grown in Minnesota, and 90% of the Sweet Tangos are also grown in Minnesota. Finish drawing the graph for this situation. All right, so 75% of a bushel of apples are Honeycrisp. So here's all apples. 75% go to Honeycrisp. And that would mean that down here would be the other 25%. And they are Sweet Tango. All right, then what else do we got? 80% of the Honeycrisps were grown in Minnesota. So we could choose one of these branches and say it was grown in Minnesota. The other one then, it just has to be the opposite, so not Minnesota. It was 80%. 0.8 to Minnesota, but then not Minnesota then would be 0.2. 90% of sweet tangos are grown in Minnesota. So sweet tangos, 90% Minnesota. And that means that we have 10% not Minnesota. Okay, what is the probability that an apple from that bushel was grown in Minnesota? So here's what we know. We know that it has, Minnesota is right here and right here. That's where it's talked about. And so we have this probability of, it's a 75% chance it's Honeycrisp, and 80% chance of that is that it's in Minnesota. So that counts for us. Let's say 75, and then 80% of that, so times 80. And these are the Honeycrisps. But we're saying that an apple, not just Honeycrisp, so also Sweet Tangos. So we'd also have this probability we have to include, and it would be, a 25% chance that it's a Sweet Tango, and then a 90% chance, if it's a Sweet Tango, that it's from Minnesota. So I just followed these trees that ended up where I'm thinking about, and I'm thinking about grown in Minnesota. All right, so we could use a calculator to finish those up. Times, okay, I got point. So overall, just that it's grown in Minnesota, regardless of the type, it would be 0.825, which is a pretty good chance. And that should make some sense. I mean, you have of the 25% of the apples, 90% of those are in Minnesota, so that's most of those apples, and then also most of the 75% of the apples, so that's pretty good. If a randomly selected apple was not grown in Minnesota, what is the probability that the apple is Honeycrisp? So we're thinking we basically need to know the probability that the honey is an apple crisp. And if you remember the probability unit, this is kind of a conditional probability. It says if a randomly selected apple was not grown in Minnesota, what's the probability that it's a Honeycrisp? It means that we already know it's not grown in Minnesota. We just want to know what's the probability, if it's not grown in Minnesota, that it's a Honeycrisp. So basically, like, what's the probability of Honeycrisp given not grown in Minnesota? But that's really not what this section is on. So an easy way to do this is to figure out how many, you need to know total number of not grown. And then, so that's your total on the bottom of a probability, total. And then whatever you're specifically looking for, your specific type. So we would say, well, to get all of the apples not grown in Minnesota, we'd have to take this route and combine it with this route, because they're both not in Minnesota. So that looks like, and that's the total, so that's like 0.75 times 0.2 plus 0.25 times 0.1. And that should give us our total, the total number of apples, total probability of the number of apples not growing in Minnesota. And then what's the probability it's apple crisp? So we would just need to know the amount of Honeycrisp that are not grown in Minnesota. So it's also fit the criteria, but it's the specific type. So just this one. And we already know those numbers. We just used them. 0.75 times 0.2. All right. And so we can just calculate that with a regular calculator. Do the top and bottom separately and then divide. And when I do that, I get 0.857. So it's about an 86% chance that it's a Honeycrisp if it's not grown in Minnesota. And that should make sense because only 10% of the Sweet Tangos are not in Minnesota, and only 25% of all the apples are Sweet Tangos. So it's a pretty small percentage that are Sweet Tangos not in Minnesota. So we would expect most of them that are not in Minnesota to be Honeycrisp apples, and they are. So this was kind of just an intro section about this new unit, graph theory, and it's not going to be as jumping around to different like types of problems as much in the future, but it's just to kind of get us an idea what is really meant by a graph. Like the graphs could mean a lot of different things. They don't just have to be XY coordinate plane, a linear, a line on that, or a quadratic. It could be a representation of a lot of different things. So there's some questions that you should go through and try them out. All right, I hope this helps. Thanks.